Hello, welcome to everyone in this video. In this video, I want to discuss the question which asked in University of Calcutta for semester 4 2021 question on analog electronics, which is CC9 paper. So if you want to watch the others previous year solution of different university physics honors question, you can go to the description box. Link are given there. The playlist link are given there. You can go through the playlist. So today's today's discussion, that is the physics honor 2019-20 syllabus, exam held on 2021, analog electronics, full marks of 50. You can go through this question, that is 1 to 1 A B C D E F G H, and then 2 A B C, 3 A B C, 4 A B C, 5 A B C, 6 A B C, and 7 A B C. Okay, so this is the total question asked in this year in this examination. I request all of you, first you try to solve this question and then continue the video towards the solution. Okay, so I think you take the pause or screenshot so that you can solve this question. After solving this question, you continue this video towards the solution. Okay, first you try to solve this question. If there is any doubt, you must comment in the comment box. So let's start. First question says, so the difference between the current voltage characteristics of an ideal and practical current source, starting the reason for such difference. For a ideal current source, the current source with a resistance, parallel resistance is infinite. But in the practical current source, the current source with parallel resistance, some parallel resistance with high value. So that's why the current output current is constant throughout any voltage. If you apply any voltage, if you measure any voltage here, you just get the same current throughout this any voltage. But here, if you apply this voltage with increasing voltage, the current is dropped, because with increasing voltage, this current also increases. So current through this RP, that is parallel resistance, the current through the RP, that is the parallel resistance current, will be increased, because this voltage by resistance, since this voltage apply is increased, so the current through this resistance also increases. So that's why this current increase, that's why the source current will be reduced, because this output current is nothing but the source current minus this current through this resistance. So that's why the output current will reduce for the practical current source. So that is the difference, and that is the cause why this current is reduced. Next question. The band gap of the specific gallium arsenide is 1.98 eV. That is the band gap of the gallium arsenide. That is, band gap means the difference energy gap between valence band and the conduction band. The energy gap between the conduction band and valence band is known as the band gap, which is 1.98 eV. Calculate the wavelength of the electromagnetic wave radiated upon direct recombination of hole and electron in this example. So when this radiation is incident within this material, this electron is jumped to this conduction band, or it can recombine to this electron hole pair. So this energy is nothing but h nu. You know, the energy is in terms of frequency is h nu. So the Eg is hc by lambda, because nu is the c by lambda. Lambda is the wavelength, nu is the frequency. So lambda is nothing but hc by Eg. So put this value of h, then the value of c. C is the speed of light, that is 3 into 10 to the power 8 meter per second. Eg is the band gap, which is 1.98 eV. If this eV converted into joule, that's why the charge of the electron is multiplied here, 1.6 10 to the power minus 19. So if you calculating this thing, you will be get this value, that is 6274.6 Armstrong. Okay, so this is the wavelength of the electromagnetic wave which need to radiate in this sample. Next question. Write down expression for the conductivity of an intrinsic semiconductor in terms of mobility and its carrier, explaining each term on the expression. So this relation is like that, that is sigma equal to q Ne mu e plus nh mu h. Ne is the electron concentration, that is the number of electron with a unit volume. Nh is the number of hole in unit volume, and mu e the mobility of electron, mu h is the mobility of hole. But intrinsic semiconductor, within intrinsic semiconductor, the concentration of electron and the concentration of hole are equal, because without any doping, the number of electron generated in the conduction band is equal to the number of hole within the valence band. This electron and hole generate actually due to the thermal agitation. With the due to the thermal agitation, number of electron generated within the conduction band from the valence band. Like this is the valence band and this is the conduction band. This electron comes from that one to that one. If there is one electron, there is one hole. So number of electron and number of hole are equal in the intrinsic semiconductor. So that's why these two are equal. If you take this as Ni, so you can take the common Ni. So this will be the final expression, that is the sigma equal to Q Ni within bracket mu E plus mu H. Mu is the mobility of electron, mu is the mobility of hole, and Ni is the charge carrier. Clear? So go to the next one. What is the fundamental difference between class A and class C amplifier? Class A and class C amplifier means when the operating point is such that in the active region this total input is converted into output with the amplified value. When this total input is converted into output with the amplified value, then this point or operating point is known as, this amplification is known actually class A amplifier. This amplification is known as actually class A amplifier. And class C, where the operating point within the cutoff region, you know this is a active region, this is a active region of a transistor, and this is the cutoff region, and this is the saturation region, right, where this is converted into saturation. So in A, this total input converted into within an output, and in class C, total input not less than 50% of input converted into output. Less than 50% of input converted into output. That's why their efficiency is greater compared to A. But in application, total input must be converted in output. This is the A actually used widely. Class A amplifier used widely. Next question. What is the significance of CMRR? CMRR means common mode rejection ratio of an op-amp. Actually, by using the common mode rejection ratio, you will be get the information about the op-amp, that is which eventually determine the op-amp ability to minimize the noise of audio. So this is the important point. By using the value of CMRR, you will be get the difference between this noise ability. You can minimize this using this value. This is the difference. So if this difference is tends to 0, lower value, then this is the most widely used, so the noise is minimized. Okay, so this is the mathematical expression. Just the main thing is like that. This is the main thing. Okay. Next question says, what is the load line? Load line is nothing but the line which is actually denoting the operating point of a linear device. This is a non-linear device, and this is the load line. You can see here it is a transistor. The equation will be like that: VCC equal to ICRC plus VCE. So finally you will be get this relation, which is the straight line equation. Okay, and the corresponding Q value is nothing but the intersection between the output characteristics with the load line. The intersection between output characteristics with the load line is known as the Q value. Next is explain Barkhausen criteria for the self-sustained acceleration. The gain with the feedback of a positive feedback is like that, where A is the gain without feedback and beta is the feedback element. So when this is a positive feedback, A is greater than A, that is the relation. This, if the input is 0 but output not equal to 0, then must be this 1 minus A beta equal to 0, that is A equal to 1. A into beta equal to 1. A is the gain without feedback and beta is the feedback element. Their multiplication must be equals to 1. This is the Barkhausen criteria by which you get the AC output without given AC input. Without giving AC input, you will be get AC output. This is the Barkhausen criteria. Next question. Determine Thevenin's equivalent circuit AB. Thevenin's equivalent circuit AB. Find the load current RL. That is the 10 ohm. So you need to find out this load current here. This question actually we already discussed in the series when we uh, solve this question, electronics question. There is separate playlist who are already see watch, you know the solution. Otherwise you can continue here. That is the, we just take this loop current, that is I1, this loop current I2, this loop current I3, and write down this Kirchhoff's voltage law equation or KVL equation. You can see here, that is in this expression there is a I1 and there is I2. So I2 minus I1 must be 1. In this relation you can see there is a I1 and there is I2. So I2 minus I1 must be equal to 1. So I2 equal to 1 plus I1. You will be get this relation from this current equation. Now for 1 loop 1 you will be get 20 I1 plus 20 1 means this total loop here. So I1 and this is 20 I2 minus I3, this is I2 and this is I3, I2 minus I3 equal to 5. So I2 minus I3 here, so just write down dividing by 5 will be get this relation, and I1 is replaced here, that is the I1 is equal to I2 minus 1, I2 minus 1. So you will be get this relation I2 and I3. For loop 3, loop 3, in this loop you will get this relation, that is 30 20 10 and 20, that is 30 I3 and 20 I3 minus I2 equal to 0. So you will be get this relation. So by sorry, by solving equation 1 and 2, you will be get this value I2 and I3 here. You need to find the value of I3, because this Thevenin voltage is nothing but the voltage across that point, that is the dash point where there is no current when this is open. So the voltage across this one is nothing but current into this resistance. So this is the current and this is the value of resistance. So you will be get 25 by 4 volt. Okay, so this is the Thevenin voltage. After getting Thevenin voltage, you need to Thevenin resistance, and this is when we find out this when this current source is open and this voltage source is shorted. This is the equivalent resistance. So these 20 are parallel, and this is within the series. After that, this 20 also parallel with that, and this is a 5. So you'll be get this is 10 and this is 10. So 10, 10, 20, 20, 20, 10 also the RT equal to 15. So the Thevenin equivalent circuit, this is 25 by 4 and this is 15. So you'll be get the load current like that. Okay, load current is nothing but the voltage by total resistance, VT by total resistance. Okay, so you'll be get this current through this load. Next question, define cut-in voltage of a PN junction diode. So this is the PN junction diode. When we apply a forward bias voltage, there is certain minimum value of voltage above which the forward current is obtained. This is the minimum value of voltage for which is required to getting the forward current. This minimum voltage is known as the cut-in voltage. So the minimum voltage is required to get the output forward current of a PN junction is known as the cut-in voltage. And this typical value of this cut-in voltage for germanium is 0.3 volt, and that of for silicon is 0.7. Next question. In the given circuit, that is the circuit, the Zener diode, what is the current flowing through 1 kilo ohm and 10 kilo ohm and the Zener diode? What happens when this 10 kilo ohm is replaced by 1 kilo ohm? The background voltage is 6 volt. So at first, when this is 1 kilovolt and this is 10 kilovolt, if you take this is in a breakdown region, when if first we consider this Zener diode in breakdown region. In breakdown region means when it is in background region sorry, background region means the voltage across the Zener diode is constant and which is 6 volt. Since this is a 6 volt and this is a resistance 10 kilo ohm, so the current through this resistance is nothing but 6 by 10, that is 0.6 milliampere. This is the current through this resistance is 0.6 milliampere, and the voltage across this 1 kilo ohm is nothing but this is 9 and this is 6. So this is 3, 6 minus 9 minus 6, that is 3 volt. So the voltage difference is 3 volt and the corresponding resistance is 1 kilo ohm. So final the current through this region is 3 milliampere. So this is 3 milliampere and this is 0.6 milliampere. So the rest current, that is 3 minus 0.6, which is 2.4 milliampere current flow through this Zener diode, because you know in the breakdown region of Zener diode current is used but the voltage is constant. So this is the answer. Next, when this 10 kilo ohm replaced by 1 kilo ohm, when this 10 kilo ohm replaced by 1 kilo ohm, the current through this region will be 6 by 1. If this is in a breakdown region, if Zener is a breakdown region, the voltage across the Zener must be 6 volt, and this resistance is 1 when this 10 kilo ohm replaced by 1 kilo ohm. 10 kilo ohm is replaced by 1 kilo ohm. When this 10 kilo ohm replaced by 1 kilo ohm, then the current will be like that, 6 milliampere. And you know this 3 volt gives you 3 milliampere. So it is not possible that is the 3 milliampere and there is 4 milliampere in the reverse situation. In the reverse situation, it is not happening when this is 3 milliampere and this is 6 milliampere. How this can be happen? If this is forward bias, this will be happen. But this is in the reverse junction. So this circuit or this Zener diode is not in breakdown region. So we can conclude that is this is not in breakdown region. That means the current through this is tends to 0. When this current tends to 0, the current flow through this 1 kilo ohm and this 1 kilo ohm. Okay. So this current flow through this one and this one. So this 9 volt apply in the across the 2 kilo ohm, 1 plus 1 2 kilo ohm. So you can get this value of current is nothing but this current across 1 and this one equal to 9 by 2 volt, that is 4.5 milliampere. Next question, what are the factors that affect the bias stability of a transistor? For bias stability of a transistor, there are three factors mainly caused, that is the reverse saturation current ICO, base emitter voltage VBB, and beta value. Beta is nothing but IC by IB, that is collector current with respect to base current, and denoting the stability factor S, S prime, S double prime, and these are the corresponding definition. We just define one here, that is the rate change of output voltage with the rate change of reverse saturation current with the other factor as remain constant. So this is the stability factor. Next question, for the given transistor circuit VBE saturation, that is the voltage of base with respect to emitter, that is the 0.85 volt. VCE, that is the voltage of collector with respect to emitter is saturation 0.22 volt. HFE, that is the IC by IB 110, is the transistor operating is saturation or not. So you need to justify where this transistor is saturation or not. You know in saturation this base emitter junction in forward bias, you can see this is in forward bias, and base collector junction also forward bias. Okay, you can see here this is NPN transistor, so this is positive and this is negative, so this is forward bias, no problem. Whether this is forward or not, you need to find out the voltage at point C, at point B. For that we can see that is the IE, that is IC plus IB is the IE, that is the current through this emitter, and IC is nothing but HFE IB. So if you put this value of IC here, you will be get IE in terms of IB, IC in terms of IB. Now use this KVL in loop 1, you can see that is 47 IB plus VBE plus 2.2 IE equals to 5 volt. So just replacing the value of IE in terms of IB, 111 IB, you will be get this value of IB like that, 14.25 microampere or 0.01425 milliampere. So the voltage at the base point B, voltage at base point B is nothing but this current into resistance plus 0.85, this voltage difference. Okay, or in terms of in this region you can also get this value, same value, 5 minus 47 into IB. If you just getting this value also, you will be get the same result. when you will be VB equals to 5, total voltage 5 minus IB into 47. Okay, you just do these things, you will be get the same value, that is 4.33 volt. So the voltage at point B, that is base, equal to 4.33 volt. Now you need to find out the voltage at point C. For IC is nothing but 110 IB. So put this value of IB, will be get the value of IC current, that is the collector current. So the voltage drop across the collector resistance. So the voltage drop across this resistance is nothing but current into resistance, will be get 5.17 volt voltage drop. So there is 9 volt. So the drop is 5.17. You will be get the value of voltage at point C, which is 3.83. Since VB is 4.3 volt, you can see here 4.3 volt, and this VC is 3.8. So this is lower. So N is lower and P is higher. That means this is in forward bias. So this is in the saturation region. I think clear the method by which we can get the. If this is not happening, this will be active region. Next question. Using hybrid parameter, H parameter, obtain the expression of input resistance of CE amplifier. So this is the equivalent circuit, hybrid parameter circuit of a CE amplifier. Common emitter amplifier is like that. So this is the input resistance, voltage source, this is current source, this is the admittance. So the input resistance is nothing but the V1 by R1, V1 by this I1, and V1 is nothing but the RI I1, and this is RR V2 voltage, and this current is I1. So dividing you will be get that one, and V2 by I2, V2 by I1, V2 is nothing but R2 RL. It's there is load and RL, because this is in negative sign, so that's why minus here. So you'll be get this one, and this I2 by I1, I1 and I2 are in opposite signs, so minus of I2 by I1 is AI. AI is the current gain, and the value of current is like that, and current gain is derived here. Current gain is minus I2 by I1 from output circuit. This I2 can be written here. You can see here this I2 can be written here, the current through this resistance and this current source. So these two are added here. You can see here these two are added here, and finally you will be get I2 equal to like that. So from here we will be get I2 by I1, and AI is minus I2 by I1. So this is the current gain. So here use this current gain expression. Okay. Next, define FET parameter and find this relation. In the FET, that is the field effect transistor, three main things here is the gate, these two are gate, this is the channel, source and drain. Here the transconductance, that is the change of drain current with respect to gate source voltage. With respect to this is gate and this is source. Gate due to gate source voltage, what is the drain current? This is the transconductor. Drain resistance is nothing but voltage between drain source voltage with respect to drain current is the drain resistance, and amplification factor is nothing but the voltage difference between drain source and the gate source is like that. So relation between the drain current is function of the gate source. So this drain current, which is the function of the gate source voltage and drain source voltage, these two voltage actually cause this voltage with between this gate source and the gate, these two are voltage. Okay. So just write down this one, and this is nothing but GM, and this is 1 by RD, and this total is conserved, current is 0. So you will get this relation, and this is nothing but mu. So these are the relation between the transconductance, drain resistance, and the amplification factor. Next question, consider the following circuit of the FET amplifier, determine the VD, that is the voltage as drain, voltage of source, VDS, VGS. So VG, that is the voltage at gate, is nothing but the divided power division power, that is 270, which is this one across this one, by total resistance into 16 volt, which is 1.832 volt. So voltage at gate is like that. So the source voltage is nothing but ID into RS, this resistance into the current through this FET. So ID into ID is given here, R is also given, so 3.6 volt. This voltage at this point is 3.6 volt, and the voltage at D point D is nothing but 16 minus ID RD. ID is 2.4 and RD is nothing but 2 kilo ohm. So finally you will be get 16 minus 4.8, that is 11.2 volt. So this is the voltage as point D. So you will be get this value of Vg, Vs and Vd. You will be get the value of Vgs. Vgs nothing but Vg minus Vs. So you will be get the value of Vgs. This voltage is Vgs. Vgs. This is the value of Vgs, and then Vds. This is the value of Vds. Okay. So Vgs minus equal to Vg minus Vs, and Vds minus equal to Vd minus Vs. So this is the answer of this question. Next question. State the difference between the depletion type and enhancement type MOSFET. In the depletion type MOSFET, there is a addition doping here in the channel, and in the enhancement MOSFET, there is no additional doping here. These are the induced, and this is the doped here. This is the basic difference. And the corresponding IV characteristic, this depletion type MOSFET can be used as a enhanced type MOSFET when this biasing is reversed. But the enhancement MOSFET cannot be used as a depletion MOSFET. So this is the depletion type MOSFET ID VGS curve. Next question. No, this is not IGVS curve. This is actually IDVS curve. In this region, this is depletion region, and this is the enhancement region. Okay. This is actually called replaced here. You cannot. You can omit this picture also. Actual answer of this question is like this. This is the answer of this question. Okay. Next, explain the help of with the block diagram working principle of a feedback amplifier. So in the feedback amplifier, this is the amplifier. If you feed it up this output within this input, this will be enhanced also. Again amplify. That's why this is the feedback amplifier. There is two type of feedback amplifier, positive and negative. Negative feedback is more important compared to positive amplifier. So if you want to find out the expression of the feedback amplifier gain, you will be get this gain without feedback is output by input. This output by input is the feedback gain. Amplification without feedback. When you use the feedback element, that is V output by V source, the total input, and this VF equal to Vs is nothing but Vi minus VF. VF is the voltage which got point from the output by feedback. So just dividing by Vi, you will get this relation, and this is rearranging that one. So this is A and this is beta. Okay. VA by VO is beta, and this is VA. Next, so the negative feedback improves stability of gain of an amplifier. In the negative feedback, the gain of an amplifier is more stable. The gain with feedback for a negative equals to like that. So if this change df just derivative this one, you will be get this relation df by af equal to this one. So the stability factor, that is the df equal to 1 by a beta, and since this is greater than 1, so this is less than 1. Okay, so the stability is of an unity is more stable. Next, what do you mean understand by the regulated power supply? Is a regulated power supply is device whose output voltage or current content constant with the variation of load resistance or load regulation. So with the change of the load resistance or load voltage, the source will be the same current or voltage. This is known as the regulated power supply. With the change of the output or the load, if there is no effect of the source, right? When the source is unaffected with the when the source is unaffected 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 sorry when the source is unaffected with the load voltage or current, then this is known as the regulated power supply. And this is the basic block diagram of a regulated power supply. There is the transformer rectifier circuit, filter circuit, voltage regulation, and this is the total block diagram. Next, calculate the voltage gain of a non-inverting amplifier. If we consider this is a op-amp and within this you can see here this voltage is applied here like that, and this is the resistance, and this is the circuit here connected. Actually this non-inverting port connected with this output, right? So this in this voltage, actually the addition of this voltage difference, so this point voltage of A point and B point are the same due to that one. So this current through that one is nothing but 0 minus Vi by R1, and which is equal to Vi minus Vo by Rf. So finally you will get Vo equal to this one, and this Vi is nothing but the addition of this voltage difference. Okay. Next, an op-amp has a differential gain AD which is 120. The input voltage applied to the inverting and non-inverting terminal like that. Inverting terminal V1 and non-inverting terminal V2, these are equal. This one that. Calculate the output voltage when CMRR is 100. So the output voltage is nothing but AD VD plus AC VC. AD means the differential gain, that is 120. AC is the common gain. VD is the differential voltage between V1 and V2, and Vc is the common voltage, that is the average voltage V1 plus V2 by 2. So you will be get 0.95 millivolt, and this is 0.1 millivolt. Since CMRR is AD by AC, mod of AD by AC, so AC is nothing but AD by CMRR. So AD is 120 and CMRR is 100, so you will be get AC is 1.2. So VO, that is output voltage, which is AD VD plus AC VC. AD is 120, VD is 0.1, AC is 1.2, and VC is 0.95. Okay, just putting this value, you will be get this one. I think clear. Next, determine lower frequency limit for the integrator circuit shown in below. Actually in this circuit the lower frequency is like that. Actually we use this formula directly, but however I don't know whether this needs to be proof or not, because this question marks is 4, right? So just solution, you can use this relation, you will get this value. Next one, draw the circuit diagram of Hardness oscillator. You need to practice this type of circuit, the Hardness oscillator and the other oscillator. You need to practice this circuit, which is important for this explanation purpose. So this is R1 R2, and this is the transistor. This CR circuit is a tank circuit, which is fed up into the input feedback. So this is the Hardness oscillator. Next is draw the circuit diagram of wind bridge oscillator. This is the wind bridge oscillator. These two are CR and CR in parallel. This is connected, not disconnected. This is connected. Okay. So and these are connected with the amplifier circuit, and which is feedback here. So at the balance condition, this R1 by R2 equal to the resistance of this one and this one. So after calculating, you will be get this relation and equating real and imaginary part. This is real and this is real, and there is imaginary part is 0. There is imaginary part is. So from this equation, you will be get the frequency of the oscillation. And at the balanced voltage of the, it must be equal to this one. For oscillation you will be get this relation, and the feedback voltage gain will be like that. So the feedback fraction equal to 1 by delta. From the oscillation condition, A equal to 1, so A equal to 1 by beta, and which is delta, which is greater than 3. So the gain is greater than 3 for the stable oscillation. Next is draw the circuit diagram of a stable multimeter. This is the circuit diagram of a stable multimeter. This is two transistor. These two are input voltage and this is output, and this is connected with the input here. So the output characteristic will be like that. These two point voltage VC1, that is the voltage, output voltage of C1, and this output voltage of C2 will be like that. So this is the voltage waveform. Here actually these two are operated with the same voltage, but they are operating with this different in the time. There is small time gap. When this is a uh, saturation, when Q1 saturation, Q2 cut off, and when Q2 saturation, Q1 cut off. These are alternating. That's why the voltage are equal to like that. So I think clear. If there is any doubt, you must comment in the comment box. You can take screenshot for the solution. So this is all about me, and this is my contact detail. You can connect with this telegram channel. This is my online platform, and this is my YouTube channel details. Go to the channel, you will get different physics related videos, some mathematics. Like this session, if you learn something from this session, share this video to your friends, other he or she also get benefit from this video. Subscribe this channel if you are in this channel. Those already subscribed, thanks for subscribing. Press the bell icon to get notification of upcoming videos. So take care. We will meet in the next video as soon as possible. Thank you.